have you ever just walked and saw a dog and thought to yourself, hey, that's a breed that I want, but what breed is that? Well, now you're faced with two options. You have option A, you can walk up to the dog owner and just ask them, hey, what kind of dog do you have? And they'll tell you it's a lab, poodle, Labrador, Chihuahua. Or you have option B, you can create a machine learning algorithm that's based on classifications and can take a picture of this dog, analyze the picture, and based on the classification or the algorithm that utilizes that classification, accurately predict the correct breed of that dog based on the specific models that you've chosen. And if you're like me who doesn't touch grass, you want to go with option B. So we do. We go with option B. We start working on a machine learning algorithm and we get to work. Python. We'll use Python. It seems easy enough. We create our own data set based on different dog breeds and characteristics that can help identify those dog breeds. Then we run our code. We're looking to measure the performance at this point. So we run it and we get presented with a table, a multi-dimensional table. And now we're stumped. We don't even know what this table is. We don't know what it's used for. We don't know how to read it. And we have no idea what we're doing. Now we have two more options. We could quit, go back outside, talk to the dog owner, and see if we can get the breed of that dog by talking to the dog owner, or we can continue to not touch grass and learn about that table. We choose B. Again, we're choosing B, and we're going to learn about that table. In fact, that table is a matrix, a confusion matrix.
No, it doesn't mean that you're confused when you see the matrix, but
it's just a way to determine how well your machine learning algorithm has predicted the data based on a result of the actual data. So if the actual data was a specific breed, you're comparing how well your machine learning algorithm has predicted that breed based on that actual data. And if it has gotten the prediction right most of the time, we'll say 98% of the time, we call that a high accuracy of 98%. It's a little confusing, I know. Bear with me here. Let me show you something. So when we talk about a machine learning algorithm or model, we need to give that model something to learn from, and we call that a data set. So the way this works is you have the three columns on the left side. We'll call those features for your machine learning model, and that's size, color, and weight. And then you have your result on the right side. Now, this is a two-class data set. So this is going to generate a two-class confusion matrix. In general, there usually are multi-class confusion matrices. We'll go through that stuff. But for the sake of this example, just to keep it simple, we'll start with two classes. And then afterwards, I'll show you an example of a three-class data set that will lead to a multi-class confusion matrix and how that might look. So for starters, we have our features, right? We have size, which is medium or small, color, which is black or brown, and then we have our weight, which is 65 pounds or 6 pounds. Based on those features, we get a result. The result is this a Labrador? And you have yes or no, binary. That's why it's two class, because there's only two results or two possible outputs, yes or no. It will become multi-class if those outputs have more to add to it. So let's say you have Chihuahua, Poodle, Pit Bull. Well, now you have three possible results, and that would be like a three class kind of thing. So that's what I mean by two class. Okay, simple enough, right? Let's take a look at how a machine learning model will interpret the data that we feed into it. And then we'll look at the interpretation and plot the results of that interpretation into a confusion matrix. So you can see that process almost in like an architectural way. Let me show you. So before we run our machine learning algorithm, we need to choose models in order to compare. These models are usually used to compare and see which one performs the best. So in this case, we're going to choose about 3 models. I won't go into too many details about it, but we might do that in another video. So the first model we're going to use is the k-nearest neighbor model. This is a model that pretty much relies on proximity. So the way it works is you have a bunch of dots, we'll say in a vectorized field, and the algorithm in this model is designed to pick almost like the center dot and then group the dots by proximity. So it kind of looks like this. The next model we're going to use is the logistic regression model. Now, logistic regression works well for this case because it's binary, true or false, 1 or 0, yes or no. And we are using a 2-class matrix, so yes or no. So logistic regression works very well there, and that's when you're just comparing the two, right? So it's either yes or it's no, and that's how that works. Then the last one we're using is probably one of my favorites because it's just looks cool, you know. But that's the random forest. Now, random forest is pretty much just a decision tree. What happens is it's a yes or no, depending on that answer, you get 2 more answers, yes or no. Depending on that, you get 2 more. And before you know it, you get a really long decision tree, as you can probably guess. Okay, these are the 3 models that we're going to use to run our machine learning algorithm. And we need to compare each model and see which one performs the best when classifying our dog breed. But before we do that, we need to understand the basics of a 2-class confusion matrix. So let's take a look at that. Okay, so this is the basic 2-class confusion matrix. Looks simple enough. Let's go through it. The actual is what your actual data set is showing for simplicity's sake. So these are the actual answers. These are the correct answers. Then you have your predicted class. So it's actual class and predicted class. The predicted is pretty much what your machine learning algorithm has output. So whatever your predicted is what your machine learning algorithm thinks it is or says it is. And your actual is what it actually is. It's that simple. Nothing too fancy about it. Now, we need to understand how to read the 4 boxes here. So in the top left box, we have our true positive. This is when the machine learning algorithm has successfully and accurately predicted something in this model. In this case, this is when the machine learning algorithm has predicted that this is a Labrador, and the actual data reflects that, yes, that is correct. This is a Labrador. Now, the second box on the top to the right are your false positives. These are when the machine learning algorithm says, hey, this is a Labrador. But when you look at the actual data, it shows that this is not a Labrador. So the machine learning algorithm guessed incorrectly, but specifically when it guessed yes incorrectly in this case, where the actual data was no. Then on the bottom left, you have quite the opposite of your false positive, which is your false negative. This is when the machine learning algorithm says this is not a Labrador, but your actual data says this is a Labrador. So almost the inverse. False negatives are pretty bad in the cybersecurity community. Just imagine this. Would you prefer a machine learning algorithm to think something is malware when it's not malware, which is a false positive? Or would you prefer the algorithm to think something is not malware when it actually is malware? So we do not like false negatives. As you can see, it can be pretty dangerous. False positives, happens. Doesn't really cause any harm to think something is malware and set up some protections against it, even if it is legitimate. Okay, so your last result is the true negative. This is when the machine learning algorithm says, no, this is not a Labrador. And you look at the data and it shows this is not a Labrador. That's pretty much a 2-class confusion matrix. You just learned it. Let's look at the results of our model since it's been running since we've been learning what a confusion matrix is. So let's look at how those models look now. Okay, so we got our 3 models. We'll say the top right is our k nearest neighbors. We'll say the top left, just in the same order, right? Logistic regression. And then we'll say the bottom is our decision tree, which is the random forest classifier. Okay, so the way we want to interpret this is we want to look at the green, essentially. We want to look at the true positives and the true negatives, because those are the times where the machine learning algorithm has guessed accurately. And then we want to look at the false positives and the false negatives to see how many times the machine learning algorithm guessed incorrectly. So if we're looking at the first one here, we see true positive 259, true negative 192. That is a total of 451 times that it's guessed accurately out of the total data set that we have. The next one we see 251 and 195. That is a total of 446 that it has guessed correctly. And then we move on to the last one, the bottom here, and that is 232 and 187, which is a total of 419. So of the 3, we would say the machine learning algorithm guessed correctly the most amount of times on logistic regression. So in this case, we would go with logistic regression with our machine learning algorithm, and we'd continue our program, our building, whatever we need to do for this algorithm. It's that simple, or at least it seems that simple. Let's make things a little more complex. I'm going to introduce a 3-class matrix where instead of yes or no, we have 3 different options. And now we have to determine true positive, false positive, true negative, and false negative. This time we're going to use a little math because it's not as simple as the 2-class. Let me show you what I mean. Okay, so this is what is known by a 3x3 confusion matrix. A little confusing, as I mentioned, but let me simplify it for you. So 3x3, think of this 3-dimensional vectorized kind of matrix, right? So this matrix has 3 classes, no longer the binary, no longer the yes or no. Now you either have a Labrador, a Pitbull, or a Retriever. Meaning in this case, a machine learning model has a 33% chance, a 1/3% chance of getting it right. And we represent that by the true positives right? So in this case, we would say for class 1, right, Labrador, we would have the green box at the top left here. If the dog was a pit bull and the actual data showed pit bull and machine learning algorithm guessed pit bull, we'd put the middle box. If the actual data was a retriever and the machine learning algorithm chose retriever, it would be the last box. So this diagonal sequence here is our true positives. And that stays true always. So if this was a 100 by 100, classification matrix, the true positives will pretty much always be this diagonal line. So little hack there, or cheat, I should say. But what about this white space? Well, this could be, depending on what you're looking at, this could be false positives, false negatives. It could be true negatives. Just depends on what you look at. Now, to better understand what those actually would be, I like to flatten a 3 by 3 into, 1 3 class matrix, 1 3 class matrix, and one more 3 class matrix. So 3 class matrix, kind of flatten it just to analyze and understand how it looks. That way, when you zoom back out and you look at it in this 3-dimensional space, it's a lot easier to understand what's happening and what's going on, and also why the diagonal here are true positives, because that's what's really important with this confusion matrix. Let me show you what I mean. So let's say we have class 1, right? And class 1 is a Labrador, right? Let's say you want to identify a Labrador. Well, if the actual data shows that it is a Labrador and the machine learning model predicts that there's a Labrador, that's a true positive. That means both match. It is a Labrador, the machine learning model was right, and the actual data was right. That's a Labrador. Now, moving on to the right here, if the actual data shows that this is a pit bull and your machine learning model still predicts that it's a Labrador, well, now this is your false positive. Your machine learning model thinks it's true, but the actual data shows otherwise. Same thing with the retriever. It's also a false positive. Moving down, we see that the machine learning model predicts that it's a pit bull, but the actual data shows that it's a Labrador, meaning the machine learning model predicted incorrectly when the dog was correctly chosen from the actual data. So that's a false negative. And again, with the retriever, another false negative. Now you have the remaining space on this initial class, I should say. In this case, because we're flattening it and we're looking at it one class at a time, we're not going to use the diagonal trick. We're just focusing on this first class. So the remaining would be our true negatives, because the actual data is showing pit bull in the middle box here, and it predicted showing pit bull, but we know it's a Labrador. So both have accurately guessed incorrectly. That's a true negative. Again, with the retriever, the machine learning model predicting the retriever and both predicting the retriever. It's accurately incorrect. So those are our true negatives. That's class 1. Let's take a look at the class 2 that we just flattened. Boom. So now, as you can see, instead of having the true positive up here, which would be the first class, we have to shift it down in class 2 to have the true positive, where the actual data is reflecting a pit bull, because now it's a pit bull and the machine learning model has predicted a pit bull. Successful. So we have true positive here and we have one at the top. So now we know, the diagonal seems to be falling in line. Even though we flattened this matrix, things seem to be working out. Let's take a look at the true negative, false negative, and false positives. So if the machine learning algorithm is predicting pit bull and the actual data is not reflecting pit bull, that's a false positive. So we have the false positives to the left and right of the true positive here. Now, if the machine learning algorithm is not predicting pit bull, so we'll say up here, but the actual data was a pit bull, that's our false negative, because machine learning model was incorrect and the actual data showed what is correct. Then we fill in the space where both the actual and predicted got the answer incorrect, which is our true negatives. So we fill that in. Okay, now you probably see the pattern here. We can move on to the last flattened class, and we should see the true positive continue the diagonal movement. And we do. True positive continues that diagonal movement down to the retriever, which is when the predicted and the actual class have both selected retriever, meaning that it was a retriever. That's what it means. And of course, going through, if the machine learning algorithm predicted something other than a retriever, but the actual data showed the retriever, false negative. Vice versa, if the actual data showed something other than a retriever and the machine learning algorithm chose a retriever, that is a false positive. And then the other space, when both the actual and predicted classes were incorrect with their choices, that is our true negatives. Okay, you just understood a flattened 3x3 matrix and you blew it back up into this 3-dimensional space where you have your true positives in the middle here. Cool. What do you do with this information? we have a confusion matrix. I told you the confusion matrix was about calculating things like accuracy, precision, recall, and other kinds of metrics that you can use for your machine learning algorithm when you're evaluating different models. But how can you actually do that? How does that even work? And where do you go from here? So this is where the simplicity part of a confusion matrix might come in, because if you know the true positives and you know all the other fields here, we can calculate things like accuracy, precision with some easy formulas, which are outlined here. So to calculate accuracy, all we need is true positives, true negatives, and then everything else. So we take the true positive, the true negative, and you divide that by the true positives, true negatives, false positives, and false negatives. And that's how you get your accuracy, which is pretty much just how often the prediction for your machine learning algorithm were true. So the accuracy is how many times your algorithm has predicted something to be true. That's it. Precision is just your true positive divided by your true positive over your false positive. That's it. You just need those two metrics, true positives and false positives. Precision is pretty much just a ratio of the correct positive predictions divided by the total predictions. So of the total predictions that were made, how many of those predictions were positive? Then you get a ratio, and that's your precision. Then you have your recall, which you need your false negative and your true negatives for. That's your true positives divided by your true positives plus your false negatives. And recall is just the total number of actual positive cases that were predicted correctly. That's it. Pretty simple. There are a lot more calculations that you can do using a confusion matrix, but if you want to get into machine learning specifically for classification, because this is very specific to classification style models, then you're going to see a confusion matrix when you go to measure the output of these models. You're going to see some kind of classification matrix, and you're going to need to know how to interpret that matrix and calculate things like accuracy, precision, recall. Maybe not so much, since the algorithm might calculate those things for you, but you at least need to know what's happening and what it's doing. Okay, you just learned the basics of classification in machine learning. Do what you want with that information.